If you still have your name things, parts, would you mind putting them out? How's your first week of classes? Yeah, overwhelming, can be overwhelming. It will start settling, I hope. So 9 credits, taking 9 or 12. Anyone taking 12 credits? I hope not. 11. I don't remember how many we used to take when I was doing my grad studies. Yeah, in the first couple of years, you want to go through all your core courses, and then it's all research after that. So. So I know the Canvas page is a little bit behind. I haven't posted the links to these videos yet. I still think the videos from the permanent videos are superior in quality. There's better audio in them and all of that. So please rely on those more so than the lectures here. It's going to be almost identical. We'll start updating the Canvas page as of this weekend and next week. It's hectic on everyone getting the beginning of the semester, so but at least you're keeping up with things. Okay, last time, who wants to remind me where we left off? You remember where we left off? Yeah, okay. We talked about the difference between scalars, vectors, and tensors and that stuff, right? And we covered a bunch of other things. So what if now someone asks you what is fluid mechanics? What do you tell them? What do you tell them? I have an idea. I'm gonna ask you to try to form into groups. Okay. Remain as distant as you feel comfortable, but form into groups, like look to your left, look to your right, behind you, whatever. Pick a person, and probably it's easier to just pick the person right next to you. Form into groups, and I'm gonna ask you a question, okay? And in the group, discuss it together, and then I'll pick randomly one of the groups, okay? And the person more comfortable in speaking or answering will give me the answer for the group. How about that? Okay, that's called an active learning method. And be as loud as you want to be. Okay, the louder you are, the happier I'm gonna feel. Like, yeah, you guys are having a discussion. Okay, so let's ask these questions. What is fluid mechanics? Okay. What is a fluid? What is a fluid? Okay. And yeah, so those 2 questions. Go ahead, start chatting. Find answers to all of these questions. Yeah. If you're not comfortable getting close to the person, I understand. Just like this one.
Fluids at least in liquid form. So you're starting where did you go to school before? Okay. That's amazing. So you study what forces yeah. Because I guess you could say it is normal. Study that makes me wonder, like, should you be
All right, time? Okay.
You know what I mean?
Do we have a volunteer group for the first question? Hafiz, go ahead.
In fluid mechanics, the study of force and displacement of material that continually unfold and after the
Okay, so you define two things in one go. That's great. So you define both a fluid and mechanics. So I would say, so like you said, it's the study of displacements and forces applied on a fluid, or how a fluid responds when subjected to forces. Okay. So what is a fluid then? So let's take the second question. Go ahead.
A fluid is something that, continuously different. But on top of that, it's something like, say, water, where if you push on, if you add shear force to it, it'll continue to
Deforming, so that goes
whereas a table will break, or it will go back to where
solid. Yeah,
Right.
solid. Okay. Or also, I've heard some of the other groups say it needs to be contained, right? No, so you need to contain. Okay. Okay, great. So last time we finished off with scalars, vectors, and tensors. Just talking about those. We're gonna speed things up a little bit. And again, this review might be boring for you, but it's gonna revisit the tools that we're gonna need to build our arsenal of mathematics to study fluid mechanics. Okay, we're gonna start by defining a vector. A vector is, and I'm gonna always try to use the velocity vector u to kind of instill in your mind that we're talking about fluid mechanics. Okay, so I'm gonna refer to vectors as u. We write it like this, and we say u is just a bookkeeping or a list of three scalars, u, v, and w, or ux, uy, uz, ux, uy, uz, or u1, u2, u3. Well, we sort of know what that means. Let me see if I still have good drawing skills, since we were using computers for like a decade now. I haven't been practicing my my drawing skills. So if this were the vector u, then the three individual components. Oh, what do you think of that? That looks great, huh? Okay. So this segment over here, we call this x, y, and z. This segment would be u. This segment over here would be v, and the projection on, do it this way, the projection on the z-axis would be w, right? It's just a bookkeeping of three components, and we write it this way, u, v, w, okay? Now, last time, you also conceptually that a vector is a magnitude and a direction, and we write this as u, the magnitude of u, times a direction. Okay. Now that direction is always a unit vector, which is a vector that has a magnitude of 1. So how do you find the direction of a vector? The direction of a vector, E, is simply the vector divided by the magnitude of the vector. Right? You've taken each component and normalized it by the size of that vector, so that gives you a unit vector. Okay? So you've taken this vector and divided it by its magnitude. The result is a vector, Ex, Ey, Ez, whose magnitude is equal to 1. Okay? So in other words, this is a redundant definition, times u over u, right? Okay, so how do you show, then, show that the magnitude of E is equal to 1? So if E is u over u, show that its magnitude is equal to 1. Simply, you could say, I take the magnitude of E. Sorry, I'm going to put a little hat over here on unit vectors from now on. It's simply the magnitude of u over u, right? Which is the magnitude of u over the magnitude of u, which is equal to 1, identically 1. You know this, just gonna reiterating some of the stuff that you've learned before. Now we still have not defined how to compute the magnitude itself. Okay. You know that the magnitude of a vector is simply the square root of the sum of the squares of its individual components. You know this. It's just a Pythagorean theorem, right? If you have so this vector C is made up of two vectors, A and B, for example. Okay, so that's the sum of two vectors gives you a vector in this direction, the resultant vector. What is the magnitude of C? It's just simply, it's the hypotenuse of this right-hand triangle, right? So the magnitude of C is simply square root of A squared, B squared. Okay, the two components. So that's in 2D. Same thing in 3D, and even if you go to n dimensions, you will learn later that this is called the L2 norm of the vector, okay, for those who are more on the mathy side of things. Okay. All right. Give you a second to catch up with the writing. There's another way to also represent vectors. It's by explicitly stating or spelling out the individual components as a formula. And that goes to say U is equal UI plus Bj plus Wk, where I, J, and K are what we call the basis vectors of the coordinate system. And that's a fancy word of saying they're the direction vectors of the components of the vector you care about. In our case over here, and in all cases, we will use a Cartesian, where does the word Cartesian come from? So I think studying math and engineering, when studying math and engineering, you should study the history and the people behind those things. So Cartesian comes from the word Descartes. René Descartes, he was a French mathematician and philosopher, naturalist, not naturalist, sorry, French philosopher and mathematician who developed the coordinate system that we call the Cartesian coordinate system. It comes from the word Descartes, René Descartes. Okay? So this is a Cartesian coordinate system. It's a simple, logical XYZ coordinate system. It's kind of easy, right? Think of this room. Look at the corner over here. You have an axis in this direction, axis in that direction, and vertical axis. Using only these three axes, you can define where Louise is located, right? So you are located about, let me see, about 1.5 meters or 2 meters from this axis and about 1.5 meters from that one. And the top of your head is about, 1.5 meters from the bottom, right? So we completely define your location using those three axes, okay? And that's the Cartesian coordinate system. Now the Cartesian coordinate system, we can also define vectors. Let me draw it over here. X, Y, Z. So now we describe everything in terms of the distance on X, Y, and Z, right? And then we define these little unit vectors over here. They are unit vectors called I, J, and K. So what are the components of I, J, K? One,
1, 0, 0.
okay. 1, 0, 0. Because its length is 1 on the x-axis. It has no length on the y-axis and no length on the z-axis, right? What about J? 0, 1, 0. And K is 0, 0. Okay. So now with that, knowing that, you can describe any vector in Cartesian coordinates using its components and saying that this u vector has ux or u in the I direction. I know I'm using u and u. It's very common in fluid mechanics, so don't let that confuse you. This u is only the x component of this vector u, okay? If you want a clearer nomenclature, use ux, uy, and uz if you want. It's up to you. I will accept either nomenclature. That's not the problem. The problem here is saying the vector u has ux in the I direction, uy length in the y direction, and uz length in the z direction. Okay? Now what's cool about vectors is you can now define other interesting things on them. You can add them, you can multiply them, you can subtract them, you can do all sorts of other things. Okay? So vector addition, simply vector addition and subtraction. So for two vectors, A, that have components A1, A2, A3, and B, that have components, B1, B2, B3, A plus B is equal to, what are the components of A plus B? You add the individual components, right? It's just you can do it also geometrically. So A1 plus B1, A2 plus B2, and C2, sorry, A2 plus B2, and C2 sorry, A2 plus B2 and A3 plus B3. Now, is A plus B a vector? Yes, it is a vector. Adding two vectors, you're going to get a vector, right? You're not going to get something else. Okay. Interestingly enough, there are going to be vector operations where you do an operation, you might get a tensor or you might get a scalar. Okay, we're going to be talking about this. Same thing, A minus B, simply A1 minus B1, A2 minus B2, A3 minus, yeah. And these are just definitions. Multiplication by a scalar. Multiplication by a scalar. Alpha A, so alpha is a scalar, just a number. Alpha A, is that a vector or a scalar? Vector, right? It has the effect of rescaling the vector, either shrinking it or enlarging it, right? And in terms of its components, it's equal to alpha A1I plus alpha A2J plus alpha A3K. Notice how I'm mixing the nomenclature, just to, again, set that in your mind that you can use either this list nomenclature or this IJK, okay? Both are identical. So now we defined additions and subtractions. What about multiplication? How can you define the multiplication of two vectors? Turns out there are numerous ways to define the multiplication of two vectors. It's not as clear-cut as the multiplication of two scalars, where there's only one way to multiply scalars. But with vectors, you're taking an operation on sets of points. Do you multiply each individual component? And what does that mean? Do you multiply the first with the second component and the second with the first component? Clearly, there's no dictated way of defining a vector multiplication. That's very important because that's up to the science and the math to define that. And you can arbitrarily define whatever multiplication operation you want to do on vectors. However, it is important to keep track of operations that are relevant to the physics, right? So some vector operations, a vector multiplication, like for example, taking A1 times B1 and then A2 times B2 is probably a useless, it's not very useful because we never see that in physics, okay? So we're gonna define two types of vector products. The first one is the scalar product. Scalar product. Also known as the dot product. There's a reason I like to call it scalar product, and you will see that in a second. But you know what the dot product is? If you have two vectors, A and B, so if you have, say, two vectors, vector A, and vector B, these are just in space, two random vectors. The scalar product, or the dot product, is written as A, you put a dot, B. What does that mean, from what you know? Go ahead.
I'm going to multiply the x component by the x component, the y component by the y component.
And add them up. Okay. That's the strict mathematical definition, but what does that mean? So, pardon me?
The magnitude of
the magnitude of,
the language.
Okay, so that you're still giving me math definitions. Okay, that's fine, because we've all been taught to think that way. Okay, and I am, I'm still the same. Sometimes someone asks me like, oh, I give the math definition. But when my kid comes and asks me, what does this mean? He doesn't ask me that. Although next year he might be. But when he asks me about what that means, I cannot tell him that, right? I need to explain to him, like, what do we mean by the dot product and why it's a useful operation, okay? So here's one way to interpret the dot product. Okay, so there's an angle here between the two, and first we're gonna just write the definition. So we have two definitions, which are equivalent. The first one, from Nick, is that this is equal to A1B1 plus A2B2 plus A3B3. And the second definition from Hafiz was, this is the magnitude of the vector A times the magnitude of the vector B times the cosine of the angle between the two. Okay? Now, before we go further, is the result of A times B a vector or a scalar? Is it a scalar or a vector? Scalar. That's why I like to use scalar product. Because it's a definition of the product of vectors that returns a scalar. There's going to be another definition that returns a vector. Okay? Now, you've all known that the dot product is an operation that measures the projection of one vector on another, right? So if you want to find the component of A in the direction of B, right? You do, what is this distance? Just physically, just geometrically. What is this distance? It's A times cosine theta, right? Gives you this distance. So this distance is simply A times cosine theta. Okay? All right, now suppose that, and this is going to trigger some physics, okay, on your part. Suppose that, I'm going to take this picture here, again, draw something over here. I'm going to put a little box over here and put a rope on it, okay, and have a sticky figure carry that box. Let's put it in the tray. I'm not a sticky figure anymore. I used to be, but okay. So this is the vector A, right? Okay. This is the vector A. The sticky figure is pulling this at an angle theta from the ground, and it's traveling a distance b. Now I'm going to ask you for some physics intuition. What is the total work done by this person pulling the box a distance b? So there's a force, they're pulling at an angle, there's this force, okay? And it's traveling a distance b. So the work done is A, magnitude of A, times cosine theta, because you want the component in the direction of motion. So if you're going uphill, you want the component of the force in the direction of motion, times b. In other words, now that's equivalent to the dot product. Okay? In other words, the dot product is giving you the work done, is telling you how much work is being done by the vector A in the direction of vector B. Another definition is, so we stick with that definition. Now, let's take a couple of scenarios. Let's look at two scenarios and deduce another definition. Now I want you to form into groups. want you to form into groups and answer these two questions. What is the dot product in the first case, two perpendicular vectors? And what is the dot product when the vectors are parallel? Okay. Do you want to work in groups? And try to interpret it. Yeah? Try to interpret the definition or what they need, either in terms of the work example, okay? Try to interpret it in terms of the work done by the force. So try to think in terms of the force, because the work done in the direction. So if A is the force vector and the direction is B, what is the work done in the direction of B? In this case, what is the work done in the direction of B? Okay. Time, and before I ask for answers, consider a solar panel that's taking radiation from the sun to generate electricity or heat the water. Okay. When is it gonna be the most effective? When the sun is perpendicular, is just directly above it, right? When the radiation is incident directly on perpendicular to the solar panel or along the direction of the unit normal of the solar panel, versus if the sun was parallel, the rays were parallel to the solar panel, so nothing is hit. Okay? All right, who wants to take an answer? You guys back, Johan?
So regarding like the work of A projected onto B, since the angle is 90 degrees, we use the definition of the dot product AB cosine theta of the cosine is 0.
Yeah, so there's no work done in the direction. So this case, it's 0. Because if you look at the force example, there's no work being done in the direction of B. And if we want to look at the example for the sun, this was your solar panel, and it had a unit vector in this direction. If the sun was directly, okay, if the sun was here, okay, then the rays of the sun are perpendicular to the unit vector, right? So there's absolutely no work done by those rays to generate electricity. This case, what about this case?
It will be A into B,
Theta.
magnitude of both.
Times?
A magnitude of A into magnitude of B.
Yes, exactly. It's the maximum. It's going to be A times B. Okay? It's going to give you the maximum amount of work that can be done by the force, or take the sun again. This is the unit vector, and the sun right above it. Then the rays are coming in parallel to the unit vector. They're going to do the maximum work. Okay. Now, anywhere in between is gonna any work or any electricity generated, whatever the sun is going to depend on that angle. This is the lowest you can get, 0. This is the maximum you can get. And anywhere in between is going to depend on that. Now, another definition, one last definition, is to say the dot product is a measure of how much A and B point in the same direction. So if A and B point in the same direction, other words, they're parallel, then the dot product is maximum. If they point in opposite directions, then they don't point in the same direction at all. So they're zero. Okay, the dot product is zero. And anywhere in between is going to tell you is a measure of how much they point in the same direction. Okay? Okay, hopefully that gives you some intuitive sense of what the dot product means. Okay. Now we can use the dot product or the scalar product, we can use it to define the scalar product can be used to define magnitude of vector, the magnitude of vector. A vector. Okay, so A dot A, we call that just simply A squared, and that's going to be equal A1 squared plus A2 squared plus A3 squared. So the square root of that is going to give you the magnitude of A. So A is going to be the square root of A dot A. Other uses of the dot product is it can tell you, it can give you the vector components in a given direction, which is what we discussed here. When you take the dot product of vector A with vector B, it gives you the component of A in the direction of B. Okay? So dot product. Actually, let me take that back. The dot product between a vector A and a unit vector, specifically a unit vector, gives you the component of that vector in the direction of the unit vector. Now remember, the unit vector has magnitude 1, so it just gives you A cosine theta. So if I just want this component, this value, okay, I need to dot it with a direction vector because I want this B over here to be 1. So in other words, the dot product can be used to obtain vector components in orthogonal coordinates. In orthogonal coordinates. So in other words, when you do A dot I, and we're using the hat for all unit vectors, that's going to give you AX. If you do A dot J, that will give you AY. And A dot K, that's going to give you AZ. Okay? And you can show that this is simply AX, AY, AZ dot 1, 0, 0. It's going to be AX plus 0 plus 0. It's going to be the same thing. Okay. One last thought. The dot product can tell you when two vectors are perpendicular. And it's also a necessary and sufficient condition for two vectors to be perpendicular. So if you were creating some tool, some device, some flow where you want to satisfy that the flow needs to be perpendicular, or the two things need to be perpendicular all the time, then you want to make sure that the vectors of those two objects are always perpendicular. Therefore, their dot product is always zero. Because it's one thing to say, yeah, I want these to be, perpendicular all the time. But when you go and try to do the math and analyze it, this is what it boils down to. Okay. So, dot product can be used to check if vectors are perpendicular. Can it be used to check if vectors are parallel? No, because when they are parallel, it's just going to give you a value. But as zero is like, oh, zero is zero, right? But if it gives you a value, how do you know that that's the maximum value you're going to obtain from the dot product, right? You don't know that. But zero is the minimum value you can obtain. So when it's always zero, you know that they're perpendicular. Okay. Now we're going to define the other product of vectors. If you're still writing, let me know. Sorry, I might go faster than you're writing. The other vector, so we define the scalar product. Now we're going to define the vector product. Yes. So, vector product or cross product. So you see, there's not a unique way to define multiplication between two vectors. Okay? Because vectors are higher dimensional beings. Okay? That was it. Anyway, okay. So the vector product or the cross product, I'm going to state the definition and then try to talk about the physical meaning. For two vectors A and B, it's written as A cross B. The dot product, we have a dot. For the cross product, we just have this X. And that is the result of a cross product or a vector product is a vector. As opposed to the scalar product, whose result was a scalar, the vector product results in a vector. And it's given by this definition of A2, B3 minus, I'll show you a little trick how to do that, A3, B2, I, plus A3, B1, minus A1, B3, K, plus A1, B2, minus A2, B1, K. Don't memorize this, there's a easier way to kind of get those numbers, get that formula. Well, I like to do it, and I learned that very early, kind of in high school, and it kind of stuck in my mind. So you write this as in this matrix form, like K, and you list the components of the first vectors, vector A1, A2, A3. Who's done that? Who's done this one before? Okay, perfect. And B1, B2, B3. So what do you do next? Pardon me? Full factor, okay. So we start, and I like to do it. Okay. I start with the I component and I take this submatrix. Okay. So for the I in the I direction, the components are just simply going to be the discriminant of this little matrix. It's A2, B3 minus A3, B2, I. Okay. Okay. Minus Now you do the j direction. For the j direction, you're looking at this submatrix. Again, do the A1, B3 minus A3, B1, J. But notice there's a negative sign here. Okay, J. And then finally, the submatrix for the K direction is this one, plus, then you take A1, B2 minus A2, B1. Okay. You've done this, right? Okay, good. Just making sure that my math is not ancient. And finally, the magnitude of A cross B. So A cross B is a vector. Okay, you want to call it C. So the magnitude of this vector C is equal to the magnitude of A times the magnitude of B times the sine of the angle between the two vectors. Okay. So by the way, I actually learned a new word today. Like there's always something new to learn. Okay. So what do you call if you have x-axis here, y-axis, okay? You have a vector A. Go down, okay? So what do you call this component? Call this the projection of A, right? The projection of A on this direction. So that's A cosine theta. What do you call this component? It's called the rejection. I learned that today. This is called the projection. And this is called the rejection. Rejection. And it's A times sine theta. Okay. Okay. Going to the vector product. How do you think we can explain the vector product? It's hard to explain, I know that, but if you have any ideas, maybe you've learned something that I haven't, and whoever taught you the math. Okay, you're saying?
So the I recall just like a cross product B, so it's follow the right hand rule.
Sure.
So the B is the I couldn't recall too much, but someone is the direction and A is something. So
okay. So you're not wrong on the A cross B. If we were to draw now two vectors, A and B, separate by angle theta. Okay. The cross product of A and B is a vector C that points in the direction of rotation from A to B, and use the right-hand rule. So in this case, A cross B points into the plane. Okay. So what do you draw over here? An X, because it's the back end of the arrow. Okay, pointing in there. Because C is always perpendicular to the plane A, B. Okay. So A and B, if you define a plane that contains those two vectors, the cross product is always a vector that points in the direction perpendicular to that plane, and the magnitude is this guy, A times B times sine theta. The reality is I have yet to find an intuitive definition of the cross product that kind of makes simple, intuitive sense. Some say it could measure rotation, which is when we take what's called the curve, that becomes very clear. It's a clear measure of how much rotation there is going on. But when you're taking the cross between two vectors, it's still not clear to me how to explain that in an intuitive manner. So I apologize for that. So we're going to stick with definitions here. But there are properties of the cross product that are going to be opposite of the properties of the dot product. Okay? So let me do one more thing here. If you're doing now, so this is the vector C over here. Now if you had A and B like this, and you take C equal A cross B, in this case, you're doing the rotation from A to B, and C points out of the board. So we show it like this because it's the tip of the arrow. The arrow is pointing in your direction, and you can see that tip of the arrow. Okay? Okay, so now the degenerate case, we're going to do the same thing we did with the dot product. Okay? What is A cross B and A cross B? And AP? Okay. Okay. You only need to look at this definition here with the angle. So if you focus only on the magnitude of A cross B, A cross B over here is going to be 0 because there's the angle between those two vectors is 0. So if you look at this definition, sine 0 is 0. Okay? Over here, it's the maximum, right? Because sine theta is 1. So it gives you the opposite story of the dot product, right? So A dot B over here was 0, and A dot B over here was max, right? It gives you, because it's based on the rejection, the opposite of the projection, right? So between the dot product that can tell us when vectors are perpendicular, it didn't tell us much about vectors are parallel. Cross product is going to tell us when vectors are parallel. So what we learned from this, the higher level, seeing the forest rather than the trees, you can hear that word as you do your PhD. Perpendicular vectors, A dot B is equal to 0. Parallel vectors, A cross B is equal to 0. To be rigorous, we're going to put a vector over here because A cross B is a vector. Okay. All right. I think I can let you go now. Thank you so much. Sorry for the crazy week. Things will get smoother. Yeah.